Hi, I'm Kevin Houston, and I've got a bit of mathematical fun for you today. Nothing deep, just a bit of maths and a bit of art. You've probably seen ASCII art before. You know, pictures made entirely out of characters and symbols. Here's an example from Wikipedia. A fish made out of text. You can see J's and V's, equal signs, and so on. Now I thought, why not take a picture of myself and turn it into ASCII art? But because I'm a mathematician, I decided that I would only use digits 0 to 9. It's not an original thought. Plenty of people have done this before. And here's the result. If we zoom in, you can see it's made up of numbers. Now, if you read all of the digits from top to bottom, you get one extremely long number. My picture ended up being just over 6,000 digits long. Okay, so mathematicians love prime numbers. Primes are the celebrities of the number world, right? Everybody has heard of them. Now, if the number representing my ASCII art face turned out to be prime, then I'd be able to produce a poster and call my picture Me in My Prime. But of course, the chances that a random 6,000 digit number is prime are tiny, so I cheated, but just a little. I could check if my number is prime, and if not, I could increase it and check to see if the new one is prime. And I just keep repeating the process again and again until I find a prime. The great thing about this process is that only the last digits change, and these are in the bottom right of the picture, a place nobody would notice. As long as I don't have to make a big change, everything is fine. And luckily, we don't have to check every number. We can skip the even numbers, for example. Now, let's talk about the maths. How do you check whether a huge number, thousands of digits long, is prime? Well, actually proving primality is hard. Multiplying numbers is easy for modern computers, but factoring them is incredibly difficult and time-consuming. So much so that the internet and banking security relies on this fact. So instead of proving something is prime, mathematicians often use tests that can quickly rule out numbers that aren't prime. Okay, so primes are the celebrities of the number world, so let's think of primes as having an exclusive VIP party. Only primes are allowed. At the door is a bouncer looking to stop composite numbers that are not prime, from getting in. Now, the bouncer can do quick checks when a number tries to get in. For example, does the number end in 0, 2, 4, 6 or 8? In other words, is it a multiple of 2? Then it's, sorry mate, you're even, no entry. What if it ends in 5 and is bigger than 5? Then it's, you're divisible by 5. Out you go. Okay? Right? So these simple tests instantly kick out lots of composites. But unfortunately, they also let some unwanted guests slip through. Composite numbers like 21 or 49 will stroll straight in, despite the fact that 21 is 3 times 7 and 49 is 7 times 7, i.e. not prime. So we need stronger tests. Enter Pierre de Fermat. This is the man with the margin too small for the proof of his famous theorem. But instead of Fermat's last theorem, we use what's called Fermat's little theorem. It tells us that if p is a prime and a is some other whole number that isn't a multiple of p, then the remainder of a to the power p minus 1, when divided by p, is 1. So, take p equals 5 and a equals 2. Then 2 to the power 5 minus 1 is 2 to the power 4, which is 16. Divide 16 by 5, then we have a remainder of 1. Perfect. That's what Fermat's little theorem tells us. The idea is that if we have a prime, then the remainder is 1. It doesn't work the other way though. If I try a different number and find the remainder is 1, the number may possibly be composite. But it works as a test because if the remainder isn't 1, then we know the number is composite. In other words, if a number fails this test, it's definitely not prime. If it passes, well, it might be prime. Or the number might just be lying. Let's see that lying in action. The number 341 looks prime-ish. If it came to the party, it would be saying, me? Yeah, I'm totally prime. Let me in. But it's actually 11 times 31. So the bouncer applies the test. The remainder of 2 to the power 340 upon division by 341 is 1. So 341 passes the test even though it's not prime. That makes it what is called a Fermat pseudoprime. The word pseudo essentially means fake, so a pseudoprime is a fake prime. That is, it's not really a prime. It just looks like one, or rather passes a test to look like one. It's basically a number with a fake ID convincing the bouncer it belongs inside the prime party. So we need something better. One of the strongest primality tests we have is the Bailey PSW test. Think of it as a bouncer running 2 different checks. One, a Fermat-style test involving powers and remainders. 2, a Lucar sequence test, basically asking the number to behave the way primes behave when you build a Fibonacci-like sequence from them. Right? Lucar sequences are like Fibonacci sequences. Prime numbers generate a sequence with certain repetitions in them. So if you create a Lucar sequence from your number and you don't see the telltale repetitions, then your number isn't prime. We're running 2 independent tests. It's like running a fingerprint test and a DNA test on a suspect. Now, the details for both prime tests are too complicated to go into here. The essence is that if a number fails either test, it's thrown out. And although we can't prove it's a perfect test, no composite number has ever been found that passes both parts of Bailey PSW. There's even a $1,000 prize if you can prove that it's 100% accurate, or if you can find a counterexample. The Bailey PSW test is built into the Python programming language, and so we can use that to check whether my ASCII selfie is prime, or at least probably a prime. It may not be prime, and if it isn't, and I can show that, then I could collect the $1,000 reward. Anyhow, essentially, I created 2 Python scripts. The link will be in the description if you want to play with them. The first takes a picture and converts it into ASCII art, and the second looks for nearby pseudoprimes. For the ASCII art, I used the Commodore 64 font, partly because it's a classic computer close to my heart, partly because the font is fixed width, which you need for ASCII art, and partly because it is a bolder font, so helps the picture not look too faint from a distance. I used 80 characters across, which is a nice balance between detail and size of number. Sure, I could have gone higher, but that would have made the numbers enormous, say 20,000 digits. The program can actually check numbers that high, but I didn't want to wait 15 hours. Okay, so the next step was to look for that prime, or rather pseudoprime, as that is the best we can hope for. The long digit for the picture wasn't prime, and I was expecting the program to take about half an hour to find a pseudoprime, but it did it in 9 seconds. Amazingly, the second number it checked passes the Bailey PSW test. Basically, I had to change only 1 digit in the picture to get the pseudoprime. Absolutely unbelievable. That I had to change only 1 digit in the entire picture still amazes me. Once I had my pseudoprime version of the picture, I decided to make a poster for display at the annual MathsJam gathering. Because of this, I added some colour. The plain version looked a little bland. Yes, it's cheating slightly. It's not pure ASCII art anymore, but it makes the poster better visually. And here it is. This is the final ASCII art on the poster. My face turned into digits, a giant number tweaked until it became a pseudoprime. All for the sake of a maths joke. Me in my pseudoprime. Thanks very much for watching, and thanks to my brother Ian for giving me some tips on how to design the poster. I've been Kevin Houston. See you next time. Bye.